The second question is whether the time budget was sufficient and anytime learning possible. To that end, we examined the learning curves. We show examples on two data sets, one easy one on the left and one hard one on the right. So on the left figure, the Carla dataset is an example of an easy dataset. Most participants succeeded in climbing the learning curve quite fast. One of them, though, PASA and GU in orange, had a slow start and then a big jump in performance, probably due to a change in model at some point. For most models, the score increases monotonically as a function of time, which can be expected if the code self-evaluates well its performance and internally decides to discard models that have a performance that decreases over time. A few algorithms fail to do that, and we observe, for instance, that the purple curve of TeamSol had some ups and downs. On the right figure, we have an example of a hard data set. The two top ranking participants in red and dark orange reach their performance asymptote, though. This did not preclude, however, given more time, that they might have adopted different strategies and reached even higher scores, because one observation is that no participant ventured in performing neural architecture search. As you may remember, our learning curves have a scaled time axis, and we introduced two parameters, the maximum time, capital T, and the time offset, T0, as can be calculated by looking at the time limits on the ALC on T0. When T0 is small, the ALC puts more emphasis on performances at the beginning of the learning curve, and thus favors fast algorithms. When T0 is large, similar weight is applied on the whole learning curve. Performances are uniformly averaged, so being a little slow at the beginning is not that bad. We recomputed the ranking of the participants for various values of T0. On the left figure, you can see ALC results as a function of T0 for one particular data set, Carla. As you can see, most learning curves do not cross, with a few exceptions. We observed that on most data sets, varying T0 had little influence on the ranking. And indeed, on the right figure, we show the overall performance measured in average rank as a function of T0. Here again, curve crossing are very rare. In particular, the red and dark orange representing the top two participants do not cross. The light orange and light yellow curve do cross. They correspond to the third and fourth place participants in the AutoDL challenge, which were declared as tied. So in conclusion, participants succeeded in applying techniques of anytime learning. They had sufficient time to attain decent performance, and some of them are really good at climbing the learning curve fast. As for the third question, we also surveyed participants and found that indeed they applied meta-learning techniques, capitalizing on the sample public data sets. This is one of the most interesting outcomes of the challenge, even though some of the meta-learning techniques are still really simple, like using pre-trained networks or initializing a hyperparameter search with the best hyperparameters of similar known tasks. And finally, we surveyed the participants who made it to the final ranking to figure out how hard it was to enter the challenge. While the majority of them found the challenge duration sufficient and the software libraries adequate, they were more divided on the computational resources and on the data format. So this gives us some room for improvement in the next challenges. And last but not least, did the participants use deep learning, even though we didn't really force them to use it? We only induced them by giving them tasks for which deep learning often performs well. Well, 100% of them indicated that they did, even though when you read the fine print of their fact sheets, they used a combination of a variety of methods, including linear models, ensembles of decision trees like random forest, kernel methods like SVM, etc. We have a paper in preparation detailing the methods employed. In the next few slides, I will briefly flash some tables to whet your appetite. I do not expect that you'll be able to read them at the speed of the talk, but you can play it back at a slower speed or download the slides from my webpage. The first table recaps the neural architectures used by top-ranking participants. The participants often used architectures that were pre-designed by themselves or others as a form of meta-learning. They did not conduct neural architecture search while being tested on the platform. There was no time for doing that. The most popular architectures were of ResNet type, but various CNN architectures were also used. And notably, non-neural architecture methods have also been used. In the second table, we inventory automated machine learning techniques used by various participants for meta-learning, pre-processing, hyperparameter optimization, transfer learning, and ensemble learning across various modalities. Finally, in the third table, we compare the techniques adopted by top-ranking participants across domains. In the next few slides, I will reveal the architectures of some of the top-ranking participant solutions. We already observed that all the participants declared having adopted different strategies for the different modalities. Still, the Team Deep Wisdom came up with a general unified software architecture. This raises the hope to be able to rationalize more and unify the approaches to various modalities in the future. This also inspired us to conduct systematic ablation studies. In particular, we identified two very critical modules that we asked the participants to disable to evaluate their importance on performance. The meta-learning module in orange and the data ingestion agent in green, responsible for loading the data fast and eventually subsampling data. We also encourage the participants to remove one of the other modules in blue, namely the data preprocessing augmentation agent, the feature engineering agent, the model selection agent, the evaluation agent, and the ensemble agent. Another team, PASA NGU, made a notable effort to provide workflows. Here we see the computer vision workflow covering both images and videos. They also unified the workflow for text and speech, and only made a separate workflow for tabular data. So this raises the hope that we could evolve towards a unified workflow of all modalities. I'm aware that I'm going too fast for you to really see the details of these workflows. I invite you, to review them more slowly. The team who proposed the most advanced methods in terms of meta-learning and hyperparameter selection is AutoML Freiberg. They use Bayesian optimization to find the best hyperparameters for meta-trained tasks. Then, given meta-test tasks characterized by meta-features, they narrow down their search space using stored performance matrices. Unfortunately, they didn't make it to the final official ranking because they turned in their last model late. Some of the results I have presented can be found in these references. The latest ones and the results of the ablation study will appear in our TPAMI paper in preparation. We are still analyzing data and running post-challenge evaluations, but what are our takeaways so far? The lessons we have learned so far are that 1. The winning methods are capable of generalizing on new unseen datasets. This points to the fact that we are well on our way towards universal AutoML solutions. 2. Domain-dependent approaches are dominant. So there are no universal workflows, and meta-learning is still handled mostly by hand tuning. 3. Because of time constraints, the participants could not afford to run expensive NAS for every new task. Thus, there is a need for transferability of learned architectures. And 4. Beating baseline 3 by using true meta-learning is hard. So we need to provide more metadata sets in future challenges and benchmarks. So what's next? Well, first of all, Our primary ongoing effort is to test winning solutions on a larger number of data sets and make ablation studies to extract more detailed information on the methods of the AutoDL challenge. We want to conduct such large benchmarks more easily, so we are concurrently developing a platform based on CodaLab called CodaBench. Secondly, we invite you to enter a new competition that just started in the AutoDL series called AutoGraph to apply automated machine learning solutions to graph node classification problems. Third, we have another exciting competition in preparation on black box optimization that we are helping to launch on the CodaLab platform. Stay tuned. And last but not least, we are preparing a meta-learning challenge with Adrien Elbaz, Frank Hutter, Zhenging Liu, Jan van Rij, Li Shensen, and Joachim van Choren. According to a classification made by Liu and Xu, code submission challenges pertain to 3 levels. At the alpha level, all that is required is to provide a trained learning machine and a method predict. Eventually, no training is needed at all. The challenge platform tests the predict method by supplying test examples and gets predicted labels in return. This is typical of CodeJam or lead code competitions. At the beta level, a method fit must be provided by the challenge participants. The challenge platform tests a method fit capable of training a model from data and turning in an alpha level method. Thus, training and testing is performed on the challenge platform. This is typical of most machine learning challenges with code submission, including our AutoML and AutoDL challenge series. At this level, meta-learning is optional. The gamma level is the meta-learning level. A metadata set containing various training tasks is provided on the platform for meta-training. A participant must apply a metafit method, which, using a metadata set, turns in a beta level method, which is then tested on new tasks also on the platform. And all this is made possible by the CodaLab challenge platform, which you can use freely if you want to organize your own challenges, and which you can customize because it's open source. We are very attached to scientific dissemination of our results. We organize regularly workshops at major international conferences. We give publication opportunities to the winners, and we have a Springer series we are editing on challenges in machine learning. Those are the blue book covers on the Springer stand last New York's conference. Finally, as I indicated, we are preparing a paper for a TPAMI special issue to which you may also want to contribute. So please join our upcoming challenges and win! With this, I terminate my presentation, and I would like to thank again my collaborators, Zhenging Liu, Adrien Pavao, and Sébastien Träger. And they worked very, very hard to provide material for these slides.